So with that said, I'd like to thank you for attending today's webinar. We're going to be talking about running MySQL in Kubernetes, presented by Percona CTO Vadim Tkachenko. Take it away, Vadim.
Oh, hi, Emily. Thank you. Do you hear me?
I do.
Okay, well, thank you for introduction, and thank you everybody for joining the webinar this late morning in California, where I am right now. So let's talk about MySQL and Kubernetes. We in Percona did a little research how to run MySQL and database in general in Kubernetes, and I would like to present you our findings and just some general thoughts how we can get to more stable and efficient work of running MySQL in this Kubernetes environment. And before I jump to MySQL, let's talk a little bit about Kubernetes itself. If you're not familiar, well, at least I expect if you join this webinar, you're somewhat familiar. But I would like to make a quick introduction anyway. So Kubernetes is defined on a Kubernetes website as a portable, extensible website, open source platform for managing containerized workloads and services. So I usually like to think about technology my own way. So when I think about Kubernetes, my versions becomes that Kubernetes is a way to automatically manage data center resources needed to run your application tasks. And if you look at a high level, I would like to think of Kubernetes kind of operating system, but not on operating system, not for the single server, but for multiple computing, networking, and storage resources all together. So it's kind of an operating system to operate all these available resources in efficient, economical, but way, but also to be able to execute your application and tasks. And Kubernetes has been around for a while. And why we are talking about this? And actually, we see a lot of raising interest to Kubernetes. And why is that? I define points why Kubernetes is raising in interest, because I think it provides a unified API to work in a really cloud agnostic, cloud independent way. So with the rise of cloud services, it's no secret I can name biggest cloud providers like Amazon, Google Cloud, Microsoft Azure. You can go and run your application, your software, or your servers on these cloud providers, but you probably would like to avoid cloud lock-in and to use some cloud independent way to manage your resources. And this is where container-based deployment, and this is where Kubernetes with its API comes very handy. And right now we see massive support from industry leaders, and I think that's because these industry leaders recognize all benefits of Kubernetes, and they really makes a difference into Kubernetes adoption and the general interest to Kubernetes technology. So Red Hat pushing OpenShift commercial enterprise distribution for Kubernetes. All major cloud providers, again, Amazon, Google, Azure provides services for Kubernetes. Digital Ocean and Pivotal. Digital Ocean announced early access to Kubernetes, and the Pivotal provides their distribution. And if you look right now in the market, probably it's already changed from this morning. Maybe right now it's more than 35 public distribution of Kubernetes. So it reminds me early Linux day again, early Linux operating system days, where a lot of different distributions finding a way how to provide a better way to distribute Kubernetes. So let's take a quick look under the hood. What happens inside Kubernetes? So let's take a look into Kubernetes, basic Kubernetes node, which Kubernetes takes bare metal or cloud server, and it manages it by allocating resources into pods. And the way to think about pod, I would name it a virtual server, but that might get very confusing with cloud server. So I define pod as kind of a virtual host. And the virtual host, it can pack multiple containers together. So containers like individual Linux processes working together on the same virtual host to handle that or another task. And there can be multiple containers in single pod, and there could be multiple pods in a single bare metal or cloud server. And all these resources should be able to work with local storage. And frankly, if you have one single bare metal server, it really makes sense to work with Kubernetes on it. So basically, when you need Kubernetes, when you have multiple resources which you would like to manage, so this kind of issue multiply Kubernetes nodes on multiple nodes, it will look like it. And some properties to highlight that container inside pod can be destroyed and restarted automatically, and the pod can be destroyed and restarted on a different node, and the pod can be multiplied this way for scaling out. So these properties we really need to take into account when we design our application, in our case, a database server, into account. So all these properties kind of great for stateless application like a web server, where you really when you really do not store your data, and you can multiply or destroy web server and move to different node. But this is not so great for databases. Well, the trick with databases, we like our data, and we want to keep our data safe. So initial releases of Kubernetes did not really work well with databases. But recent improvements, especially in areas like with stateful set and the persistent storage, I think that this development really put Kubernetes to consider databases as first-class citizens. And now, having all these features in Kubernetes, we can look what we can do to make it work well with a MySQL database. And Emily, I think converting my slides to PDF, I lost one picture. So let me switch it to my original Google slides, and please let me know if it works okay. So yeah, so I switched it to my Google slides. So with the way to look on Kubernetes with databases, that we with databases we rely on shared persistent storage. So the way we really expect from Kubernetes to provide a convenient and a uniform way how we can work with shared storage, that even we move our pods from one node to another, we still can access our data, and our data is preserved and safe. So, and this we are able to achieve only if you have access to some kind of shared storage. So let me switch back to my PDF slide. So let's talk a little bit about MySQL and Kubernetes. And when we start looking into MySQL, actually to start a single MySQL instance is very easy. It's actually even available in a basic Kubernetes documentation. You just go install MySQL Docker container to be from MySQL distribution or from Percona server, and you pretty much ready to go. You can access database, update data, execute queries, and run some simple WordPress application. The complication comes when we start looking to more complex setup. And again, in a professional database world, we need to provide multiple solution to for databases to serve production workload. So with databases we need to provide a high availability solution. We want our application to continue to work even if resources become unavailable, or if Kubernetes reschedules MySQL pod from one node to another. We need to rely on persistent storage. Again, we love our data, and we would like to keep it safe and available. And in case if something worse happens with our data, we wanted to keep backups and recovery strategies for our data. Now, when we speak about high availability and multiple MySQL instances, the question about traffic routing comes. How we find and detect MySQL instance which handles our traffic. And also interesting question about monitoring. We still would like to provide basic or not very basic way to diagnose and to be able to see what happens inside of our database deployment. So in our research, we come up with this more complex setup where we rely on multiple MySQL nodes. In our case, we use a Percona X3B cluster, and later I will explain why. We need to use a proxy SQL instance for traffic routing needs. We would like to use a PMM server to provide with monitoring capabilities, and we rely on backup scripts and volumes to be able to perform backup and recovery operation. So a small disclaimer, or whatever solution I will show you later, is we still consider this as a proof of concept, and we consider you can use it as a guidance for your own setup, but please do not treat it as a production ready product. And I provide you a link to our current work. This is our Percona Lab GitHub repository. You can find it on Percona OpenShift name. So let's talk about different components we consider it, and research for our solution. And the first is replication. And for MySQL replication options, there are currently three big options on the market, I would say. That traditional MySQL replication, old and solid and proven. There is a group replication, I would say a relatively new solution from Oracle, and there is Percona X3B cluster. The challenges with traditional replication, it does not provide automatic failover. If we need to perform new master detection, it can be quite complicated. And again, remember with the Kubernetes, it can shut down and move pods around different different nodes. It will assign new IP address. So if there is no way to do it automatically, we would need to script it, or maybe use third-party tools like orchestrator from GitHub. But it all kind of adds complexity to the solution. And there is also no automatic slave setup when you would like to scale out existing nodes. You again would need to script this out and do proper testing. Another available solution is a group replication. We played with it a little bit. My assessment is that it's still not mature enough to be seriously considered for production usage, and there is still no automatic slave setup with all consequences I mentioned before. So we really think that Percona X3B cluster is a great fit for to be as baseline replication for deploying all MySQL instances in a cluster. With Percona X3B cluster, we provide a guarantee that all data, all nodes communicate together through group replication. They keep all data consistent between nodes. And back to a point about automatic slave setup, PXC includes this out of box. So when you need to join a new MySQL instance, this is PXC takes care about it by itself. So Percona X3B cluster kind of solves. It was not designed originally for Kubernetes, because back in 2011, when we started to work on this product, we did not think about Kubernetes and the containers. But with all these characteristics, it all kind of comes very handy to be baselines for solution for Kubernetes. And Percona X3B cluster also provides multiple ways to work with your data, either to provide full state transfer or incremental state transfer if your node was disconnected for short period of time and restarted. Then you would need to it will need to catch up only incremental data set and to not perform whole data copy. Okay, let's talk about storage considerations. So storage options. There is in the Kubernetes propose. Kubernetes in current state propose you two ways to work with storage. There is local storage, which often can be fast and in cloud or bare metal. You can attach local SSD or NVMe options. But Kubernetes is still, I would say, quite limited in handling local storage. And again, when we speak about instance migration from one node to another, local storage is only available on local node. So in case of instance migration, the data will be lost. So this is where we rely on network storage in Kubernetes. If it's supported by your cloud or your on-premise setup, and it's supported by major cloud providers. But if you have Kubernetes on-premise, you still need to rely on some reliable network storage like Ceph or maybe commercial storage across a network solution. And in this case, the solution provides management and the flexibility required for Kubernetes. And with databases, we rely on database provisioning of persistent volumes. So whatever network plugins, whatever storage plugins and the storage setup you have for databases, we consider that dynamic provisioning of persistent volumes is required. So make sure you have it. As for traffic routing questions, well, I mentioned that we in our solution we rely heavily on proxy scale. And why proxy scale? In our experience, it is a very high performance MySQL proxy. It provides capabilities for query routing, and it supports automatic failover, which again quite important when your node migrate and start on different node. We would like application. We would like this to be as transparent for application as it is possible. So there is no downtime in handling your production traffic. So if you're not familiar with proxy scale, this quick introduction. Proxy scale works in front of, in this case, in front of MySQL traditional replication master slave setup, and with your application accesses proxy scale, but proxy scale behind scenes is capable to route your queries either to master, or it is important to write queries to master, or it is capable to route read queries to one of available slave. Proxy scale, yes, proxy scale is capable of providing read-write split functionality, which one of the most common use for query routing. Yeah, and the same applies for Percona X3B cluster, where we can define as one node as a writer, and the proxy scale will route write queries to this node, and we can define and the other nodes will be defined as readers, and the proxy scale will route select queries to those nodes. So our solution on Kubernetes OpenShift includes a combination of Percona X3B cluster plus proxy scale working in front of our cluster. And for monitoring solution, we integrated our Percona monitoring and management with some limitations, but we are working to resolve this limitation right now. And again, you can find our solution on OpenShift, Percona OpenShift repository in GitHub, and you can clone it. It is totally open source. So you can clone it and play it around. So before jumping closely to our solution, I would like to talk a little bit about the deployment options available in the Kubernetes. So I see right now most popular options is manual deployment, where you, in the traditional deployment in Kubernetes, you have YAM or JSON files where you define your deployment, and then you deploy with your Kubernetes commands. Recently, Helm charts were quite raised in popularity, but now we see more and more software vendors and database vendors switching to new way of deployment, this operator. So let's talk a little bit about each of those options. And the manual deployment, I would not say is very popular, especially for production setups. It's a kind of fine if you want to try and test and set up again a single instance MySQL with local storage. You can do that. But when we speaking about complicated setup with multiple MySQL nodes and the proxy SQL in front of it, you would need to jump a lot between different YAM files, and it is very complicated and error-prone solution. And what really makes it more complicated than needed, I would say that doing it through manual YAM files, you combine your deployment logic and the configuration parameters all together in single YAM files. So it makes it very hard to manage and configure your setup. So this is where Helm charts come into place. And Helm charts are defined as a package management for Kubernetes. And they really do well. They separate configuration parameters from deployment logic. And the way I think about Helm charts is, if Kubernetes, back to my analogy, if Kubernetes is operating system for cloud, then the Helm chart is like RPM, Debian package. But with all of that convenience from Helm charts, new way of deploying complex setup becomes more and more popular. This is operator. And CoreOS defines operator as a method of packaging, deploying, and managing Kubernetes application. And at this moment, this is most advanced way of deployment your setup. But problem is this requires probably some major software engineering efforts. And problem why does it require engineering efforts? The way to think about operator, at least the way I think about operator, is operator goal is to replace human in typical operations. So by itself, it assumes some high degree of automation. So whatever operations human performed in the past, operator is going to take on itself, and it requires quite a lot of work to make it right and properly. And there is pictures to show benefit of operator. I should give credits to Red Hat OpenShift documentation. I copied, pasted this image from their website. So the goal here is to show that operator should be able to handle much more operations than Helm charts are able to handle. Then current state of our work, which is available on GitHub, we initially focused on the Helm charts, so that's what available in our GitHub repository. But we recognize our benefits and the current trends to provide operator for complex deployment. So that's what we plan to look into in the future. On this, I will want to show a little demo of our current work. So, and if you want to play with our examples and our files, there is some assumption to highlight. Well, I assume you already have a Kubernetes running either from cloud providers or on your local premise deployment, but we don't go into details how to set up Kubernetes by itself. Again, we rely a lot of persistent volumes and on the dynamic provisioning of persistent volumes. So make sure your Kubernetes setups does provide that. Otherwise, you will not be able to deploy our files. And the current limitation for Percona monitoring and management, it requires containers to be run with some software under root inside the containers. Well, we don't require a root for your host server, but inside the containers, some PMM components still requires root access. So, how to start? So, let's start with monitoring. First, we would like to start to initialize our monitoring server. And again, please make sure that your setup allows running from root inside container. If your current setup does not allow it, for example, I know that OpenShift does not like it out of box. That you might skip this step. And we recognize it's not a recommended practice, and we are working to provide a fix for this. And given that, install monitoring then becomes a simple one command line. You instruct Helm to use our charts, and if you would like to adjust some values, this is where really separation logic from configuration comes into place. In the values files, you can adjust some parameters required for you, and you should be able to start our monitoring service. So then, by it should start again monitoring service, and it should allocate a local IP address, and it is configured to allocate external IP address also. So you actually can go and try this address right now, and it will be available a few hours after the webinar. But after that, I'm going to shut it down. I will give you 1 minute if you want to kind of type that address into your browser and see that how Percona server, Percona monitoring and management server was deployed. Okay, now moving to next slide, and now we would like to start our cluster. And again, this is a single command line. where you go and install cluster with name. Well, I was not very creative with name. It named my cluster one. And this command, as simple as it is, it behind the scene will start 3 nodes. 3 is a configuration parameter which you can change in the value CM file. It will start 3 Percona XRB cluster nodes, each node with a PMM client, and it will start a proxy scale instance, and it will configure proxy scale to route your traffic. And you can see the result of this work by checking out current pods. You will see we already have running our monitoring service and the proxy scale are in front of three cluster nodes. So as simple as it is, I would like to highlight what's going on here. So with a simple command, we are able to start multiple MySQL nodes, and Kubernetes will handle node failure and will make sure we're running as many nodes as we asked. So if some node failed by some reason, Kubernetes will find and schedule new resources to run that node. We also started and configured proxy SQL in front of 3 nodes, and we added all these nodes to be monitored under PMM server. And you may say, what's a big deal about it? With reasonable efforts, we can all script it in Ansible playbook and use it in our setup in a similar way. But what I would like to highlight here is that Kubernetes is cloud agnostic, doing this in cloud agnostic way. So or it provides uniform API and approaches when write once run anywhere. By that, I mean, if you have your deployment files prepared and you tested in on one cloud on Kubernetes, there is a very good chance that you will be able to repeat, to reuse the same Helm charts and deployments on any other cloud or even on the premise deployment. Well, again, given that you have requirement with provisioning storage I mentioned. So now we can take a look at what's going on inside our cluster. So if we check pods, we can see that we're running one proxy scale instance and 3 Percona XRB cluster nodes, and we can check available services. In this case, we know that proxy scale acts as a MySQL service, and it exposes ports to provide access, provide endpoints for a MySQL application, and also it provides ports to proxy SQL admin. So we should be able to log in inside the proxy SQL, and if we request proxy SQL to show currently running servers, we see that we have three MySQL servers. One of them configured as a write node, and the 2 others are configured as a read node. And what happens now? We would like to test what happens if we want to kill if one of the nodes become unavailable. So in this case, I intentionally killed one of pods, and I will not show you a live demo, but basically, if you would check current status, you will see that node was terminated. and after that, actually, Kubernetes will restart it. So if after that we go inside the ProxySQL, we will be able to see some new configuration. We can see that our previous server, which we killed, become offline hard, meaning that ProxySQL can no longer access it. But also, we can see that ProxySQL added another server, which Kubernetes scheduled and started behind the scene, and that a new instance joined the existing cluster and also registered itself in ProxySQL, and ProxySQL made reconfiguration to locate one of nodes as a writer and two other nodes as readers. Another possibility which is available out of box in Kubernetes, you actually can scale it up or down if you want. So we can use a Kubernetes scale command, and we can increase our current nodes from initial 3. In this case, we are asking 4 nodes. So if you do that, we again can log into ProxySQL admin to check MySQL current MySQL service, and we can see there still one dead server, but 4 nodes are available. One of them is configured as a writer node. So that's kind of to highlight what work we have done so far, and that you can go and play around with it by yourself. But we are obviously not stopping here, and we are starting to look into how we can provide MySQL operator to handle all of above plus more, and we're looking actually how can we add encryption both at rest and end-to-end to our Kubernetes deployment. I know encryption is in very high demand for enterprise deployments. And with encryption, we also need to look into key management, how we manage and integrate encryption keys with inside Kubernetes. And there are a couple additional resources I would like to point. There is already some work done on operator front from Oracle, and it is still marked as alpha quality, but it's available on Oracle GitHub. And there is another operator from Press Lab. They also provide their MySQL operator on their GitHub. So you may want to check these projects. And Emily, I'm coming to the end of my presentation. Emily asked me to remind everybody that Percona Live Europe is coming soon. It's going to happen in 2 months in Frankfurt. So please join us, and we can talk about the current state of Kubernetes and the current state of database and cloud at that conference. So please join us if you can.
Thank you so much.
And yes, thank you. That's all from me, Emily, and I'm ready to take a few questions if there is any.
Yeah, we've got quite a few. Our first question is about proxy SQL. Could it work without dropping connections over internet, or this solution only for high-speed channels?
So if I understand correctly, well, ProxySQL can work obviously over internet, your query response time obviously will be limited by a response time for connected nodes. But in Kubernetes, if you're still speaking about Kubernetes, you really deploy all components together. So I don't really anticipate you would use deployment where proxy SQL is very far from your MySQL deployment. But if this question in general, then in general, proxy SQL can connect to MySQL instance on any distance from itself.
Thank you. So our next question is, could you please tell us what's your dynamic volume provisioner of choice?
My dynamic volume provisioner of choice. Well, this is where you rely on your available solution. So if you use Google Cloud comes with its own dynamic provisioning. If you use Amazon, Amazon has its own. And if the question about on-premise, that's a kind of a hard question to answer. I think there is maybe no best choice available, and there is still work to be done in the Kubernetes ecosystem to come up with good one.
Thank you. Our next question is, PVC does not seem to be working consistently. How are you handling those issues? Kubernetes, PV, and PVC, we're seeing issues where storage attachment is not very reliable in 1.9.6.
So I think this is where Kubernetes developments comes. Speed of Kubernetes development, we rely on it. That you mentioned Kubernetes 1.9, but there is already Kubernetes 1.11 and 1.12. So we rely that Kubernetes engineering would fix this issue. When on the storage layer, we rely on underlying infrastructure or cloud infrastructure or Kubernetes infrastructure available.
Okay. Well, it looks like actually we've gone through all of our questions. I'll give everybody back a couple minutes back in their day. Thank you so much, Vadim, for presenting today, and thank you everybody for attending today's webinar.
Okay, thank you everybody. Have a good day.